We now use the expression of dG to learn about the effect of pressure on the Gibbs energy, while we keep the temperature constant, that is, while dT equals to 0. The expression of dG equals VdP minus SdT becomes dG equals VdP. And for 1 mole of substance, we can write dG per mole, or dGm, equals molar volume V sub m times dP. As we would like to integrate this equation, we realize that depending on the phase of the substance, the molar volume may or may not depend on pressure. So 2 cases need to be considered. The first case we examine is that of the solids and liquid phases. Phases we call incompressible because it is generally acceptable to assume that their molar volume is independent of pressure. In this case, the integration of dGm between an initial pressure Pi and a final pressure Pf yields Gm at Pf and T minus Gm at Pi and T equal to V sub m times Pf minus Pi, since the integral of Vm dP is equal to Vm times the integral of dP. The second case is that of ideal gases, which are highly compressible and for which we can use Vm equals RT over P. As before, the integral of dGm between an initial pressure Pi and a final pressure Pf yields Gm at Pf and T minus Gm at Pi and T. The integration of RT over P dP yields RT times the natural logarithm of Pf over Pi. On the next slide, we will use the above expressions of G versus P to compare the behavior of solid, liquid, and gas phases. On the previous slide, we derived expressions for the variation of the Gibbs energy G with pressure, assuming that the temperature was constant. These expressions show that for all phases, Gm increases with pressure. It does so linearly with pressure for solids and liquid phases. So for the solid phase S, we can write Gm of S at pressure P is equal to Gm prime of S at pressure P prime plus molar volume of the solid phase times the difference in pressure P minus P prime. For the liquid phase, we write Gm of L at pressure P equal Gm prime of L at pressure P prime plus the molar volume of the liquid phase times the difference in pressure P minus P prime. For the gas phase, the molar Gibbs energy increases logarithmically with pressure. We can write that Gm for the gas phase G at pressure P equal Gm prime for G at pressure P prime plus RT times the natural logarithm of the ratio P over P prime. The variation of Gm with pressure is shown on the left side for the solid phase in red, the liquid phase in blue, and the vapor phase in green. To define the phase that is most stable in a given range of pressures, we recall the result we obtained earlier in this lecture. Specifically, that the most stable phase is the phase with the lowest molar Gibbs energy. Examination of this diagram indicates that the gas phase is most stable at the lowest pressures. At pressures above the condensation pressure, the liquid phase becomes the most stable phase. As the pressure increases further, we reach the crystallization pressure, P sub crist, where the solid crystalline phase becomes the most stable phase. We know the existence of 2 specific pressures, P condensation, where the gas and the liquid phases are in equilibrium, and where the molar Gibbs energy of the gas is equal to that of the liquid, and P crystallization, where the liquid and the crystal phases are in equilibrium. That is where the molar Gibbs energy of the liquid is equal to that of the solid.